Okay, there we go. So welcome back. This is Monday, October 12th. Today, our topic is very focused. We want to make you excellent at graphing the 6 trigonometric functions. And I think I can show you a really nice procedure to do that uses graph paper in a very, very practical way. And you can be using your graph paper or my graph paper on the site, either one, but you definitely need to be using graph paper if you're producing graphs. Let's get right into it. I want to show you a way to easily mark the key points of all 6 trigonometric functions. I've got a series of handouts. I'm just letting some more people in the room here. I've got a series of handouts on my website showing you the 6 trigonometric functions. So I'll just slide by those right now. I'm sharing my website here. And right now we're in week 7. And we're talking about handouts in week 7. And down here under applications, I have a handout that shows you all 6 graphs. And then I have 3 handouts that help you graph them by pairs. Sine and cosine graphs look very much alike. Tangent, cotangent graphs look very much alike, slight difference. Secant and cosecant, again, look very much alike, just slightly different. Also important is the exact values of the trigonometric functions. I'll show you all these handouts in a second. But I made one more piece of graph paper that might help you draw things very, very well. And that is, look at this, rectangular grids, 3 wide rectangular grids. If you follow that link, then you'll see this paper right here. And the idea is the trigonometric graphs repeat themselves over and over again. They're what's called periodic. They repeat themselves after a fixed time. And so by giving you these 3 wide graphs right here, I hope to help you show me a couple of periods of a given trigonometric graph without crowding or making your points too close together. And that's what I'm going to demonstrate. I can demonstrate on this paper. I can demonstrate on my ordinary graph paper. I don't mind if you use ordinary graph paper, but I want to show you a specific way to use it. If you have these handouts handy, they'll also help you today. The trigonometric functions, the exact values for every 15 degrees. And remember, you know these 3 famous triangles, 15, 75, 90, 30, 60, 90, and 45, 45, 90. For the purpose of graphing today, really we can do with just these last 2 triangles, 30, 60, 90, and 45, 45, 90. They're going to make our graphs so accurate that we don't need any additional points. But in this chart, I gave you the exact values every 15 degrees up to 90, and I gave you the approximate values every 15 degrees up to 90. So we might use some of these approximate values when we're marking graphs today. You might have been looking at these graphs yourself last week as you were practicing drawing them, working on the homework, getting ready for the next homework. The 2 homeworks, the one due on Tuesday and the one due 1 week from Tuesday, are all about graphing the trigonometric functions. We always graph the trigonometric functions in radians, and we clearly mark and label the axes that we're using in our graphs. These are really old pictures I produced, but still they tell you about the basic shape of the trigonometric functions. Sine and cosine really look alike. In fact, you would think they were identical if you didn't see that one of them has been slightly shifted over. Now, was the cosine graph shifted to the right or was the cosine graph shifted to the left? We'll use those words today, but it really doesn't make a difference which one you pursue. Let's just say, let's take the sine graph as our starting point. going through the origin 0, 0. The sine of 0 radians is 0. The sine of 0 degrees is 0. But the cosine of 0 radians is 1. So sine and cosine follow the same gentle up and down mountain and valley, but the cosine starts at the mountaintop and the sine starts at sea level, so to speak. Sine goes up, back to middle, down, back to middle, and then it's done one cycle or one period. Cosine starts high, goes through the middle to low point, to the middle to the high point, and that means one period. Notice on the sine and cosine graphs here, I've graphed an additional sine wave to the right, an additional sine wave to the left. So what I'm displaying here is 3 periods of sine. Similarly, 3 periods of cosine. Tangent has its own unique shape, and the tangent is sine divided by cosine, and that introduces breaks in the tangent. For anywhere the cosine is 0, like pi over 2, sine divided by cosine is not defined. I'll have this asymptote or break that the graph does not cross. It's like a wall. So the tangent graph shoots up ever closer and closer to this wall, going on forever, but never crossing that wall. And likewise, on the other side, shoots down at minus pi over 2, where cosine is also 0. Ever downwards, forever, ever closer and closer to that vertical line at minus pi over 2. And then the tangent repeats. Interesting is the tangent starts at the origin like sine, shoots up, and then comes back through the bottom, shoots up, and then comes back through the bottom, shoots up. How long does it take for tangent to repeat itself? Well, if you count from center to center, tangent shoots up and comes back to where it started. You see that it takes pi units for the tangent to repeat itself. And for that reason, tangent has a period of pi. Every trigonometric graph has its own period. Sine and cosine repeat after 2 pi units. Tangent and cotangent, I'll show you the cotangent graph in a second, down here. Tangent, cotangent graph repeat every pi units. Notice the tangent graph goes up from left to right, and the cotangent graph goes down from left to right. These two graphs in the middle, secant and cosecant, they are the reciprocal of cosine and sine, respectively. Now, what does reciprocal mean? Wherever the sine has a value 1, then so does the cosecant, because 1 over 1 is 1. But wherever the sine is 0, like at 0 and pi, there's another asymptote. 1 over 0 is not defined. Another wall that the cosecant runs into. Where the sine is 1/2, the cosecant will be 2. That's what reciprocal means. And I'll show you how to draw those dots. Secant belongs to cosine. It's the reciprocal of cosine. So secant is built on top of cosine, like cosecant was built on top of sine. So you could think of sine and cosine as this dotted blue frame that you're building cosecant and secant on. You can think of the cosecant and secant shape as essentially an U, almost like a U, except a U that goes on forever and never stops, a very tall U. Relatively flat in the center where it touches the sine or cosine graph. All these graphs you can reproduce on your calculator. In fact, what you produce on your calculator should look exactly like what we've printed on this paper. If you set your calculator window to the same windows that I've described here. Now for uniformity, I made each of these graphs go from minus 2 pi to 4 pi, from minus 5 to 5, just so I had one similar box that I could build them all inside. But I'm really interested in the box that contains one period of these 6 functions. Notice secant repeats itself after 2 pi, and cosecant repeats itself after pi. For example, secant, the reciprocal of cosine, starts at 0 and 1, the point 0, 1, shoots up, comes back through the bottom, peaks, goes down forever, and then comes back from the top to height 1 after 2 pi units have elapsed. Cosecant comes from the very top and then bottoms out at height 1 and value pi over 2, then shoots back up, comes back through the bottom, tops out at height minus 1 and 3 pi over 2, and then shoots back to the bottom, coming back on the other side. So you see these two U's, maybe you want to call it a U and an N, maybe you want to call it a unions and intersection symbol, whatever way you like to name it. These two U's form one period of cosecant or one period of secant. One more thing that's really important before we get started, and that is you need to now fully make the conversion to thinking in radians. We practiced and played with radians a little bit last week. You were thinking about them, converting, talking about different things like angular velocity, linear velocity, arc, angle. But now it's really important that you think in pieces of pi, 1 pi, 2 pi, 3 pi, 4 pi, and then fractions. Half of a pi is pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2 is 2 pi. And then further, pi over 3, 2 pi over 3, 3 pi over 3 is pi. Let me show you what I mean on my paper. And let's start drawing. Okay, back to the video on the paper. So let's graph the 6 trigonometric functions beautifully. And let me show you how to make the very best use out of your graph paper with a box. It's going to be 0 to 2 pi, so capturing a period, and minus 1 to 1, capturing the high and low points of sine and cosine. Let's look at this box very closely. And I've way overdrawn the units on this just to help you see pi being chopped into pieces. So here's 0, 1 pi, 2 pi. And you notice on my graph paper, you can even count the grids. So I want to show you the grid marks, really important today. Each pi, I cut into 6 pieces, 6 boxes. So I drew 6 boxes and labeled it pi, and then I drew 6 more boxes and labeled it 2 pi. That makes it really easy for me to cut pi into pieces on my paper. For example, each box, 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6 is 1 pi. I want to make it really easy to cut pi into fractions. And I've labeled pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, 4 pi over 6, which is 2 pi over 3, 5 pi over 6, and 6 pi over 6, which is a full pi. I also like to cut pi into halves, and I like to cut halves into quarters. And notice pi over 2 is at 3 boxes. So one thing that I'm going to have to estimate is pi over 4. But if pi over 2 is 3 boxes, then pi over 4 is just 1.5 boxes. When you draw these boxes for me today, and when you make your graphs on the homework or exam, you're not going to write down the name of every fraction like this. You're basically going to focus on starting the box, ending the box, and the middle of the box. Likewise for the vertical axis. I want you to draw a box that's 4 boxes high. And I want you to label the center 0 and +1 and -1, 2 boxes up and 2 boxes down. So I want you to label the horizontal from 0 to 2 pi with pi in the middle and marks at pi over 2 and 3 pi over 2. I want you to label the vertical axis with 0 in the middle. 2 boxes up is 1, 2 boxes down is -1. This is going to give me a really good perspective on drawing sine and cosine. And let me illustrate this. On our webpage, I already showed you these handouts last week. Not these graphs, but 3 handwritten handouts called the graphs of sine and cosine functions, the graph of tangent and cotangent functions, and the graphs of secant and cosecant functions. If you click those links, then you see these explanations here. And I showed you this explanation last week. This is an organized way to draw sine and cosine. What I want to show you is that if we expand the boxes a little bit wider and cut things by 6, then it'll give you a very nice way to add easy dots to this graph. Same handout for tangent and cotangent, showing 2 full periods, 2 repetitions of both tangent and cotangent in 2 pi units. And that shows you that the period of tangent is pi. And same handouts for secant and cosecant, showing you that secant and cosecant each repeat themselves after 2 pi. So if you want to focus on these dots and these shapes, these skeletons a little bit more, you can look at these handouts. Okay, let me go back here. Let me go back to my paper. Let's go to another paper and draw a graph of sine and try to illustrate the procedure I want you to use. So let's graph y equals sine x. And let's say we want to graph 2 periods. Before you draw an axis and try to fit your graph to the axes, let's get a view of what sine of x should look like by drawing this box. It's 4 units high and 3, 6, 9, 12 units wide. And again, don't draw this unless you're using graph paper. And you can get graph paper anywhere from our website, Staples, Walmart, Office Max, whatever is handy for you. If you got a friend with a printer, if you don't have a printer, then ask them to print you sheets of graph paper, or just buy a pad of graph paper like I'm looking at here. It might be like $3 for 50 sheets. And it might be more. I don't know what it is. It depends on, you can get spiral bound notebooks. I mean, maybe Walmart would be the cheapest. Maybe Staples a little bit more expensive. Let's mark this box at 1 and -1 and 0, pi, and 2 pi. Now, right now, I'm not going to make this box any busier because that would be distracting. But I know the values of sine from this exact value handout. I know that sine starts at 0. I know that at pi over 2, sine becomes 1. And then I know along the way, after those first 90 degrees, sine repeats itself as it cycles forever around the circle. So sine starts at 0, and by the time you get to 90 degrees, or pi over 2, you've reached 1. Then sine goes back down to 0. Then sine dips to -1, and sine raises back to 0. This is the poem that I gave you last time we met. Middle, 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 high, middle, low. In other words, sine starts in the middle of the box. In between these two middles, you go high on the box. In between these two middles, you go low on the box. So this reflects the fact that sine of 0 radians is 0. Sine of pi over 2 radians is 1. Sine of pi radians is back to 0. Sine of 3 pi over 2 radians is down to -1. And sine of 2 pi is back to 0. Now think about these points in between. When you have your unit circle, and I just drew this circle casually, and you go 30 degrees. You know from your 30, 60, 90 triangle that the sine is 1/2 30, 60, 90 triangle, but I look up 30 degrees is 1/6 of pi. This exact value chart is kind of useful. So here's pi over 2 at 1, but I've cut pi over 2 into 3 pieces. Here's pi over 6. I need a value of 1/2 at pi over 6. This mark right here is pi over 6, 1/6 of the way to pi. How about if I take 30, 60, 90 triangle and I stand it up on its tall end? Then the sine is √3 over 2 divided by 1. A √3 over 2 divided by 1 is about 0.866. If you think about this, and that sounds like an odd number, but after you get used to placing this dot, you won't think about that number as odd anymore, right? This is 0, and this is 1. That makes this first dot at 1/2. Now what's half of a half? That's a quarter. That means this dot, this place where I'm pointing my pen is 0.75 high. Well, what's half of a half of a half? That's an eighth. And an eighth is about 0.875 exactly. So 0.866 should just be a little bit less than half of a half, or 1/8 of the way to 1. Now you can put it pretty close to that line and you're going to draw a fair drawing. But do you see now how beautifully the sine is shaped? And all the points in sine are just going to repeat themselves. First backwards for 2 pi over 3 and 5 pi over 6. And then upside down at the half mark, and nearly at this line, at the bottom, nearly at the bottom, half mark, and back to the starting place. I gave you 5 values of sine right here. But using the fact that the sine repeats, what did we just draw? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 dots. 12 boxes, one on each end makes 13. And think about it this way. If you've drawn these dots in this pattern on your paper, I defy you to draw a bad sine graph. Just trace these dots gently. And you've drawn a sine graph that no person, that no machine could do better at. I'm speaking a little bit casually, right? Because, a machine would do it faster. But that is a perfect graph of y equals sine of x. It shows the period of 2 pi units, and it shows what we call the amplitude. Amplitude is how far does it deviate from the center. Sine and cosine graph have a natural amplitude of 1. Now, if I wanted to draw this with a couple of periods, all I'd have to do is repeat this box and transfer it to a nice piece of graph paper. But before I try one of those, let me show you how to modify this in a simple way. Let's say I want you to graph not sine of x, but this time 3 times the sine of 2x. I'm trying to show you some examples that are similar to your homework. What does the 3 do? What does the 2 do? Let's think about it logically. If sine previously waved between 1 and -1, then multiplying this by 3 will only make it wave more. It'll be waving 3 times as high as it used to. That means I could change these values to 3 and -3, and still would be centered at 0. That's an easy fix. Now the sine of 2x right here, how do I view that? I want to think of that as not one wave in 2 pi units, but actually when you put the 2 here, it means you get 2 waves in 2 pi units. What it means is every value of x you used to sit in here, you're going to visit twice as fast. Now, when people write basic sine graphs like this, a sine x, bx, they often describe the period as 2 pi divided by the absolute value of b, and they describe the amplitude as the absolute value of a. Whatever this number is in front, take the amplitude of it is absolute value of that number. So this has an amplitude of 1. Whatever this number is in front of the x, take 2 pi divided by the absolute value of that, that's the period. So this graph has a period of 2 pi. That's the technical definition of period and amplitude. But the practical definition is, now let's make my graph. Let's make my beautiful box. 4 units high and 12 units wide. The practical definition of amplitude and period is that the 3 has just tripled the height of this box, and the 2 has cut the length of this box by a factor of 2. It's divided every number in this box horizontally by 2. I divide every number by 2. I get 0, pi over 2, and pi. So that the period of this graph is 1 pi, and the amplitude of this graph is 3. The most it deviates from a center is 3 units up and down, and it repeats itself as soon as I've gone through pi units horizontally. Now, what's the beauty of this? Having labeled this box, I fill in all the dots that I used above in the exact same way. Starts middle, 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 end middle, middle high, middle low. And now these independent boxes, like one box over 1/6 of pi is at 0.5, and similar 0.5 is one box from the center. 0.5, 0.5, except now 0.5 originally in here, 1/2 means what? Minus 1.5 in my new scale. 1/2 in the standard box, black, means now 1.5 or 3/2 in this stretched box, the scaled box. Do you see what I do when I deal with period and amplitude? I am scaling, this is the fancy word, I am scaling the graph. Scaling the graph means stretching it or shrinking it, horizontally or vertically. Now let's fill in the other dots. What were the dots on the second box? What were the dots 1/3 of the way to pi? 0.866, but times 3. Oh, what would that be? 2.5, 2.6? You know, I'm not really interested maybe in the number. What I'm interested in is that it's nearly at the top of that curve. And likewise for his partner on the other side. Nearly at the bottom, nearly at the bottom. Look at that. What you've drawn is the exact same curve and the exact same dots. Except you've scaled the horizontal and vertical elements of this box. Now let's take a piece of graph paper and make a really nice picture of this for, let's say, 2 periods, maybe even 3 periods. So now I can lay down some axes possibly. Let's make a really nice drawing laying down some axes, and maybe I'll use pencil here so that I can focus on something if I have to erase it. Okay, what about this graph? Centered at 0 still. So let me put my horizontal axis dead center. The wave starts at 0 still. So that would be my vertical axis, my y-axis. I want to allow 12 boxes from left to right. So let's put my vertical axis here, where I can easily get 12 plus 12, 24 boxes. I don't know if I've done that yet. So let's count. 3, 6, 9, 12. 3, 6, 9. Look at that. I came up one silly box short. You know, I could move this axis one box over. Maybe I should. I could add carefully one more mark on this side. Maybe I should do that. But plan yourself so you can get 2 times 12, 24 boxes from left to right here. And if you want to stretch this up to 3, you can. Let's stretch this down to -3. You can. Or you could just call these 2 boxes 3 and -3 on the graph. Let's do the first one, calling this 3 and this -3. I'm imitating what I did in this box here. Let's call this what? 1 full cycle is going to be pi. Let's call this 2 pi, 1 pi, 3 pi, 4 pi. It's kind of interesting. If I messed with this scale right here, I could have called this 1 pi and 2 pi. Maybe I should do that. I think I'm going to do that just so I measure exactly what I did with the box. That's why I'm using an eraser and a pencil. So let's call one period 12 boxes a full pi. Let's call my second 12 boxes 2 pi. And now let's just put in these red dots. 0. Pi over 2, back to 0. 1 full pi, back to 0. In between the two middles is high. In between those two middles is low. Then I have a half, nearly high, a half, down a half, nearly low, 1 half. And there's a full period of pi in this graph and a full amplitude of 3 up and down. Now I repeat myself for the next period. Middle, high, middle, low, and then half, nearly high, half middle, half down, nearly at the bottom, half down. And here's 2 perfect graphs of y equals 3 sine 2x, 2 perfect periods. You got to connect the dots now. Just lightly shade these dots together. Don't try to force your pencil to draw a curve because then your pencil skips. Just shade through the dots like you're shading a drawing. I don't know how much art classes you take. This is actually very helpful when you're drawing something like this. And then you draw this beautiful smooth figure. You can add more scale if you like. After you do some practice, maybe you could make this actually look taller. But this is an accurate drawing. Name the axes. Maybe you could name some of these in-between points. If this is pi, let's call this pi over 2. If this is pi and 2 pi, then halfway is 1.5 pi, 3 pi over 2. This would be enough for a good drawing. Your question is like, how does that mesh against the calculator? Now, I could actually, remember, I could go backwards some boxes, right? So I want to make this look like my calculator maybe. Let's go to pattern down here. So from middle, I'll go to low, and then back to middle, and then I'll go half, nearly down, half, middle, half again. So see how easy it is to repeat that pattern. But if we want to check this against the calculator, I bet you we can make this look exactly alike. So I'm going to type in on this calculator, just I'll get rid of something else I was doing. Get rid of something else there. 3 times the sine of 2x. I should make sure I'm in radian mode, right? So on the mode key, let's check that I'm in radians. No, I'm in degrees. Let's switch it to radians. I like the color on the screen, but I acknowledge that the letters are too small. So I can deal with that with a book or two. Well, let's move to radians. And then let's graph. Now, how does that look to you? It looks wavy. It looks up and down. It looks like we were doing it on the paper. But then again, it looks slightly not like the paper. So let me show you how to make it look exactly like the paper. And then you'll have extreme confidence you got it right. Let me see how close I can move this to the camera. How do I make it look exactly like the paper? I use the scale I used on the paper. Hard to show the paper and the calculator at the same time. But let me slide it back and forth with a book. And a paper. So do you see the scale I chose in this picture? I went all the way out to 2 pi on the right. How did I go backwards? 2 boxes of 3 is minus pi over 2. So this last dot here must be nearly minus pi over 2. Then I want a little bit farther down. So if I want this graph on my calculator to match that graph on my paper, what do I have to do is tell the calculator only to draw that much. I think the calculator drew too much. How about the height of this graph? Well, it's nice that you see that the tick marks are like 1, 2, 3, if you look closely, but still that's so small, it's hard to count those. So let's take my window and change the X values. Let's change them from minus pi over 2, and I can literally type in minus pi over 2 to 2 pi. I can literally type in 2 pi and let the calculator figure out what the exact number is. How should I make my scale? Do I want to show every one of these tick marks that I've made? What are those tick marks worth? Well, here's pi over 2. Here's pi over 4, which is half of pi over 2. Why don't I put tick marks like I did on this paper here? Why don't I mark every pi over 4? Again, for my X scale, I just type in pi over 4. Now, Y, I know is only going to go as high as 3 and as low as minus 3, not minus 10 to 10. I don't need that. But why don't I give myself a little more room so I can see the thing comfortably? Why don't I let my minimum Y be minus 6 and my maximum Y be 6? And I can keep the Y scale at 1 if I like. How does this look compared to what we drew? That looks much nicer. In fact, that's almost a dead ringer for what we drew, right? Except the fact I went a little bit over on the left side here. Here's another goofy thing, right? Do you see that I used 2 boxes to represent 3? I was doing that so that I could use my box method here, but the calculator has no such restriction. The calculator just says, okay, I'll mark 3 boxes with 3 tick marks. I've drawn 2 full periods here and a little more on the left. So make sure you give someone as many periods as they want when they ask you to draw something. And I've marked and labeled my scale better than the calculator marked and labeled its scale. Although I could see that someone could like complain, well, I'm not used to counting 2 boxes equals 3, 4 boxes equals 6, 6 boxes equals 9. Well, that's true, but you could adjust to that. Okay, let's go to the next level. I'll set my calculator aside. Let's draw the graph of, okay, here's the reason I don't like this graph paper. Some of the graph paper is like really porous, and when you draw above it, it bleeds through. Let me get another pad of graph paper here that doesn't bleed through so easily. Depends on what pad of graph paper we want to use. Well, if you like to work in the wood shop, you got a lot of tools in your garage. If you like to graph things, if you're a math teacher, you got a lot of different kinds of graph paper. Maybe that's obsessive, but let's try this one. I don't think this will bleed through. Let me show you how to graph something slightly different. Let's go for a cosine graph this time. Let's give it a funny period of pi. Let's Create an amplitude which flips it upside down. And then let's really go whole hog. Let's add a number 3 in front. Okay, I'm going to draw the graph of 3 minus 2 times the cosine of pi x. And each one of these numbers does something for me. Remember, this number in front of the x tells me the period. The period will be 2 pi divided by whatever number that is. Now that's pi. Absolute value of that is pi. So this graph will have a period of 2. Next, this number in front tells me the amplitude. But don't say the amplitude is -2. Remember, the amplitude is the absolute value. How far does it wave up and down from the center? This amplitude is 2 also. And last step, what does this 3 do? Well, that takes the whole cosine wave and just lifts it 3 units. This is called a vertical shift. When you shift something, you just move it over, except this time I'm moving it up 3 plus 3 units. Let's put all 3 of these together. It repeats every 2 units. Its amplitude is 2. It's vertically lifted 3 units up. And one more thing. I need another color. This minus sign here says what? Even though the amplitude is 2, this minus sign here like flips the graph upside down. It's like vertically reflected. Every point that used to be positive when it comes out of here is now negative. This is a vertical reflection. Or if you want to say it in plain English, the graph is upside down. Now, before you say, whoa, that's too busy, I can't deal with that. How am I supposed to draw that? Let's just go back to our beautiful box method. Let's draw a box that's 12 units over and 4 units tall. 12 units over and 4 units tall. These are like little tick marks I'm making. What I'm making is kind of a baby sketch of this graph. Now, ordinarily, cosine floats between -1 and 1, and horizontally from 0 to 2 pi. I even know that cosine starts high, ends high, in the middle it's low, and then the middle it's middle, and bends down like this. Now, this is a very rough drawing. But what does the vertical reflection do? Instead of starting in the upper left, now it's going to start in the lower left, excuse me. And then it's going to go, instead of the low point at the middle, it's going to go to the high point. And then it's going to go back to where it started. Now that's an ordinary graph of cosine. In between the high and the low, it's in the middle. And you see these 3 boxes. What is it between a middle and a high point? First, it's halfway, and then it's nearly at the top. Nearly at the top, halfway. It's coming back down. Halfway, nearly at the bottom. Halfway, nearly at the bottom. So that this is one wave of what an upside down cosine looks like. Just carefully scratching in a beautiful smooth curve. Now, when I've given you these dots, like high, high, low, middle, middle, no triangles. If you draw a sine cosine graph like this, you get pretty much 0 points. You want to draw this smooth, beautiful curve. I tried to mention this on our website. You want to draw something that looks exactly like the book. Now, what's the problem with this? This is just the graph of an upside down cosine graph. Amplitude 1, period 2 pi. I need to make these changes, but it's very easy to make those changes. Watch that. The amplitude is 2, right? So instead of +1, -1, now I'll stretch as high as +2 and as low as -2. So I've done the amplitude. Check. What about the period? I've got to divide each of these numbers by pi because this period is going to be 2 units, not 2 pi units. Divide each of these numbers by pi. I get 0, 1, and 2. Here, when I multiplied each number by 2, I got -2, 0, and 2. But here, when I do the period, I take the number in front of the x and divide the natural numbers by that. The natural numbers of 0, pi, and 2 pi, I divide by 0. I divide by pi, give me 0, 1, and 2. So now I've dealt with a period. Check. I already turned it upside down, right? That's vertical reflection. Check. Let's do one more thing. Let's vertically shift it. And what does that vertical shift do? It literally lifts this graph up 3 units. But I'm going to show you how to lift it up by doing what? Adding 3 to each of these numbers. Now I'm at 5 for my highest point. My center point will be at 3, and my low point, 3 plus -2, -2 add 3 would be a -1. I'm sorry, it'd be a +1. Now I've got the perfect blueprint for drawing this cosine wave. And I'm just going to take it to a giant set of axes. So I imagine that my vertical axis starts right alongside that 0. Notice what your vertical center is. This thing is not centered at 0 vertically anymore. The horizontal axis is not at 0. The horizontal axis is at +3. It's been raised 3 units. So if this is my center of the graph, that's been made to be 3 units tall. So where do you want me to put my axes? Maybe I have to put my axes here. 3 boxes downward. And my vertical axis there. Okay, let's finish drawing my box. I need to do 2 units, one way or the other way. 1, 2, right? So I can mark 2 units over here. Let's compact this a little bit. Let's make this 1 unit, and this 2 units, and this 3 units, and this 4 units, and this 5 units. Let us draw several periods. Every 3 boxes, I made 1 unit. Here's -1 units. My box is going to go as low as +1 It's going to go 2 units over, and it's going to go as high as 5. So now let me take this box and put it inside there. And what do? Start low, end low, middle high, middle, 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 middle. Now I'm going to go a third of the way over and half down, and a third of the way over and nearly at the bottom, a third of the way over, half up, and a third of the way over nearly at the top. And do you see from the center, this is 1.5 boxes. So a third of the way over was 1/2 of a box. Instead of 1.5, 1/3 of 1.5 is 1/2. But all I'm really doing is gently putting in the points on this wave. Let me make another box. Someone says they want 2 periods out of this. So I'll go up to 4. And you see, the silly thing is, that's 6 boxes wide. I can go as many boxes as I like, left or right. I can make boxes this way, 1, 2, 3, 4, 5, 6. Now I'm going to draw that box outline kind of light. Now drawing it with pen, I drew it a little bit too dark. But now I'm just going to repeat my points. Low, low, high, middle, middle, low, low, high, middle. Now I'm making these marked precisely in the middle, right? But I'm just repeating the pattern. And now I'm going to put in the in-between parts. Halfway down, almost at the bottom. Halfway up, almost at the top. Halfway up, almost at the top. Halfway down, almost at the bottom. The funny thing is, your eye and your hand are exceptional at drawing patterns. You just need to be told the pattern. And I'm telling you the pattern is low, middle, high, middle, low, back to the beginning. And then a third of the way over, halfway down, nearly at the bottom, halfway up, nearly at the top, nearly at the top, halfway up, nearly at the bottom, halfway down. I don't even want to, how many points did I do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 24, and then 36 and 48. Do you understand? You just drew 48 points. I just drew 48 points. And now I'm just going to gently shade them in. And sometimes you get people being critical of your graphs. And I will be picky about your graphs. But do you see here, if you draw all those points in and then just gently shade, no sharp triangles, gentle curves, if you draw all those points in and then just gently shade through the points, you can draw a graph that no one else could draw better. You could draw a graph that the machine couldn't draw better. Now the acid test is, does your calculator like it? I'm being a little bit silly in that sense. Calculator doesn't make the answer right or wrong. But if you could draw this on your calculator and get the exact same image, that's going to be a powerful evidence that your graph is good. So let's type this in the calculator, but here's the secret. Let's type the scale into the calculator that I used, right? Now that's going to go over here to -2, and even up here to looks like 6. How about up and down? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. 1, 2, 3, 4 boxes down. If you like, I'll go 5 boxes down. The beautiful thing is, with this pattern that we used, if I type that function into the calculator and tell the calculator how to draw the screen, I'm going to see exactly what I drew on this paper. Then you got some belief that you're right. Let me slide my book in here. I don't want this one. What's my graph? 3 minus 2 times the cosine of pi. Just use the pi key for pi. The pi key is over here above the division symbol. Sorry. It's right here above the division symbol. X. Okay, so that's what I'm supposed to draw. Let's see if the calculator likes our drawing. So I'm going to go to the window. And how am I going to run this window? From -2 to 6. No fractions of pi. Just from -2 to 6. And let's make my marks on the calculator screen every 1. I don't want to make marks every third. That's too busy. Make marks every 1 unit. X scale 1. How am I going to run my Y scale? -5 to 10. That'll still give me a good picture. And do I want to make a mark at every unit? That's what I did on the paper. So let's try it. Let's make the Y scale 1. And this is what I want you to achieve. When I press the button, I'm going to bet money that this graph looks like my graph. If I'm in radian mode, of course, I need to be in radian mode, which we are. But now let's press the button. This is very satisfying. And the first time you think about this, you say, no, I cannot draw that well. I cannot draw as good as a calculator. I need the calculator. Well, guess what? You drew just as good as the calculator. Even better in a way, because you're telling me what those marks mean. So you can actually draw perfectly. Sine, cosine, secant, cosecant, tangent, cotangent. Oops, sorry. I was missing somebody, so I just added them. You can draw each one of these curves perfectly, just about as perfectly as any human could draw it. You can see on this, sorry, destroying my camera. You can see on this graph units 1, 2, 3, 4, 5. The center is here at 3. If you want to emphasize the center, you could even draw a graph of a line that's at 3 high. Goes right through the center. Okay, let me get out of here. Let's draw something else. Okay, this is our mission today, to only draw sines, cosines. We'll get into a tangent and secant in a second. But I've got to do one more thing. And that is, there's one more change I can put you through. And that's going to be reflected here in next week's homework. I can stretch this or shrink it vertically. That's called vertical scaling. I can stretch it or shrink it horizontally. It's called horizontal scaling. That's a period. I can lift it up or down with a vertical shift. But I can also pick the graph up and move it left or right with a horizontal shift. Let me show you what a horizontal shift is. So I'll do secant, cosecant, tangent, cotangent in a second. Let's stick with sine and cosine just so we get the method. Let's try the graph where I'm going to horizontally shift something. And since I'm horizontally shifting, let's not add the vertical shift. Let's just do some regular graph shifted over. So I'm going to say 4 times the sine of two x minus pi you'll know what each one of these pieces means, except for this then time I've added something being subtracted from the x here. You know that this is the amplitude. And you don't take the number there, like -2 in the last problem. You take the absolute value. So this thing goes up and down 4 units. You know that this number tells you the period. Take 2 pi divided by the absolute value of that number in front of the x. The period is 2. Pi divided by 2, period is 1 pi. We've already drawn that. But now this number right here, and I'm not ready to display it yet, this number, subtracting pi from the x, causes a horizontal shift. And in order to recognize that horizontal shift, what I have to do is not ask, what am I subtracting from x times 2? I need to know what I'm subtracting from x itself. Don't say you're subtracting pi from x. You're subtracting pi from 2x. Let's rewrite this so that I see what I'm subtracting from x. If I factor out that x times 2 is make 2 factored out here. What number do I put here so that it's equal to minus pi? I have to put minus pi over 2. Seems kind of crazy to like invent a fraction. But when I multiply this out, isn't it 2x minus pi? 2 times x, 2x. 2 times minus pi over 2 is minus pi. This tells me what the horizontal shift actually is. This subtraction causes a shift to the right. But this tells me what that horizontal or phase shift actually is. The fancy word for a horizontal shift is called a phase shift. And you don't take the minus sign with this number, you just take the number itself. What am I subtracting? I'm subtracting pi over 2. Say that to yourselves when you're looking at a phase shift. What am I subtracting? A little bit too crowded there. Now we're ready to do our box. And now look at the beauty of this box. The beauty of drawing this box is I'm doing every problem in a uniform way. 12 boxes over, plus minus 2 boxes. Ordinarily, that gives me an amplitude of 1, deviating 1 from the center, and it gives me a period of 2 pi. But now, I'm going to make these changes. The amplitude of this graph is 4. So this is going to go as high as 4 and as low as minus 4. I just multiply every one of these numbers by 4. This 2 is going to do what? Shorten the period. It's going to give me 2 waves and 2 pi. So this 2, I'm going to divide every number here by 2. 0, pi over 2, and pi. But now this last number, the phase shift, tells me where I'm starting. Where am I starting? What am I subtracting? Where am I starting? I'm subtracting pi over 2, which means I start this box not at 0, but at pi over 2. This pi over 2 here means I add pi over 2 to each one of these things that I just scaled. Pi over 2 plus 0 is pi over 2. Pi over 2 plus pi over 2 is 1 pi. Pi over 2 plus 1 pi is 3 pi over 2. I've done all this and I haven't told you what it looks like. Well, what does it look like? It looks like a sine wave. What does a sine wave look like? Starts middle, ends middle, middle middle, middle high, middle low. Those are the stars of a sine wave. Do you know right now, and this is not about trigonometry, but if you guys like watching stars, do you know right now is a very good time to go outside at night and watch the stars, because you can see 3 planets. In this past several days, you get to see 3 planets in the sky. If you go out around, you can watch them all night, but at 9:30, you'll get a good, around 9:30 to 10:30, you'll get a good view of 3 planets. Due east, there'll be a very bright star in the east of the horizon, about 40 degrees up, but it's going to be very noticeable because it's got a red tinge to it. That's Mars. Directly in the east, and it peaks around 10:30, but it's going to be up for some time. You'll see it after sun goes down, about 7:38. Then if you look almost due south, a little bit to the southwest, as the evening progresses, you'll see, I got to keep them straight in my head, Jupiter and Saturn. And they're going to be, again, extremely noticeable because they're too large and too bright to be stars. They don't have a red tinge to them, but I think if you look southward around 8 or 9 o'clock, well, maybe 9, 10 o'clock, you'll see one large bright star, and I believe that's Saturn. And then a little bit above it and to the left, you'll see another very bright star that I believe is Jupiter. But I know you see 3 planets. I just forgot whether it's Saturn and Jupiter or Jupiter and Saturn. The brightest one, the largest one will be Saturn, and Jupiter will be above left, equally bright, a little bit smaller. But the thing that's obvious about those 3 planets, Mars, Saturn, Jupiter, is they're way too large and way too bright to be a star. So right now is just a very good viewing time if you like viewing stars. You could even see them inside a city when there's too much light. Go check that out tonight, somewhere between 9 and 10 at night. The reason I'm mentioning this is because these dots that I've drawn the sine curve on, they're like stars. When you go out at night and you see 3 dots in a row, what do you call that? It's called Orion's belt. There's another constellation called Orion, the hunter. I don't think I could draw it very nicely, but you could find a picture online. And the easy way to recognize Orion is to look for the 3 stars that line up, Orion's belt. And at this time of year, this doesn't get to the sky. So it tend to be around in the north, I think, kind of towards the north and west, but it doesn't get to be high in the sky till very late, maybe after midnight, 1 or 2 in the morning. You got websites that could tell you exactly when these things happen. I want you to learn these stars. I want you to learn the stars of the sine or the cosine. I want you to learn the stars of the tangent and cotangent and secant, cosecant. And what are the stars of sine? Middle, 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 middle high, middle low. And then in these three boxes, as you ascend, you go halfway, you go nearly at the top, halfway, halfway down, nearly at the bottom, and halfway. And you could name all of those points on any particular graph yourself or with a calculator. But all you have to do is connect those graph dots to make a beautiful sine wave. Okay, let's take it down here on my graph paper and draw it very neatly. And let's draw something that kind of fills up the window here. And I knew I was going to go -4 to 4, right? So let me mark those in true units, -4 to 4. Let me show you how to translate these dots in the box, which I only use 2 boxes up and down. Let me show you how to translate them to a wider, taller box. And I want to start at pi/2, right? So I don't know. I don't think there's any harm in calling that pi/2. And this will be pi, 3 boxes, pi/2, 3 boxes, pi, 3 pi/2, 2 pi. So this is pi, 3 pi/2, 2 pi. But now focus on my box. The box is going to go from pi/2 to 3 pi/2 and from -4 to 4. So the box is going to be right here. Ah, do you see what I did? I made -4, 3 units down, and -4, 3 units up. That's terrible. It's ridiculous. My box looks bad. You know, if that happens, you just toss it. Especially if you drew in ink. Let's try it again. I mean, don't be afraid to erase. Don't be afraid to start over on a new piece of paper. Let's try it again. We were feeling so confident. Okay. Let's mark from -4. See, now this is what you call being consistent with a scale. You can't make the scale 4 boxes is 4 units and then 3 boxes is 4 units. That's inconsistent. So I want to make my scale consistently, right? And then I was going with my pi/2 at 3 boxes. Pi, 3 pi/2, 2 pi. And now I feel better if I draw my box. Plus -4 and exactly pi units long. Starting at pi/2 and moving to 3 pi/2. In fact, since I intend to draw some more boxes, why don't I just add another box here? I'll go over another pi units. From 1.5 pi, that's 2.5 pi. I could go backwards, 3 boxes and 3 boxes, and make the graph over here. And that would be backwards minus pi/2. You see what I'm doing? I'm just prepping. Now, you could object, you saying, oh, you got this beautiful wide box up here, and now you've scrunched it. Okay, let's scrunch the points. Starts middle, ends middle, 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 middle high. Now that's at 1.5 boxes again. Middle low. And then a half box is halfway, and 1 box is nearly at the top. Now I did scrunch this severely, didn't I? But if I follow the same pattern and faithfully reproduce these dots, Excuse me. Okay, I got off track right there. Just shows you have to be careful. It's hard to talk and draw at the same time. And faithfully reproduce these dots. And I've got this beautiful sine wave. That's a little bit squished. Maybe it even looks a little bit triangular, but it's not a triangle. This is a beautiful, gentle curve. Starts middle, ends middle, 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 middle high, middle low. Then a third of the way, half, third of the way, up near the top, half, half, near the bottom, half. Beautiful sine curve. Gentle, smooth sine curve. What your point of view on that is? I mean, is it perfect? Is it nearly perfect? Well, it's perfect enough for our work. And let me just emphasize this again, that I can always check on the calculator to see if I've got this graph decently right. Let me slide my calculator over here. That's better. Okay, so last thing to do today, let's just graph this as I wrote it. And bringing it down. There, let's get it all on one screen, hopefully. 4 sine 2x minus pi. Type it in just like that. 4 sine 2x minus pi. And then you'll know if you did that factoring right. I don't need that 3. Let's do my window. What's my window? Minus pi over 2 to 5 pi over 2. Just type in minus pi divided by 2 to 5 times pi divided by 2. The calculator figures out what number that is. What's my scale? I'll make marks every pi over 2, it looks like. So pi divided by 2. Now what's my vertical scale? Minus 4 to 4, yeah? But let's be generous and let's go down to 6 negative and up to 6 negative. It's up to 6 positive. Just so I have this thing like nicely sitting in the window. Minus 6 to 6. Count by ones. Graph. And I don't even have to wait for it to finish. That's a perfect match. Well, maybe it'd be a more perfect match if I made it red. And so this calculator allows me to change the color, which I think is a little bit of overkill. Yeah. Here's red. Okay. After bragging about it, I've got to see my red. Red. Oh, I got to go down here and say, okay, that's better. Okay, a little bit of overkill there, but there's my beautiful red graph. I want to graph the other functions with you too, sine, cosine, tangent, secant, cotangent. But what I need to do first is make this box method absolutely solid in your mind. And the handouts that I put on my website also talk about setting up these boxes for all 6 functions. So you practice, and this is related to your homework that you're due tomorrow. You can graph and identify any function now using this box method, sine and cosine. And then next time we'll practice secant, cosecant, tangent, cotangent. Okay. Katoria, if you had a problem with the audio, maybe you fixed it because you got the thumbs up. I think my audio is recording and the recording will have it, but in case I didn't notice that earlier, I apologize. Okay, I've got to go over to another meeting. I'll see you guys on Thursday. This is going to be a regular week, back to 2 days a week. And we'll talk more about you getting ready for your exam. In the 9th week, this is the 7th week, we'll talk more about you getting ready for your exam and practicing these graphs. I'll have this posted later this afternoon so you can enjoy it again and again and again. All right, just it's a little joke. Have a good afternoon.